Okay, we're going to continue on here and talking organic, I think. So last time we got into talking about how to go about naming organic compounds, especially our alkanes. Remember, pretty much even our alkanes and everybody else, essentially you always want to, when you're naming, is always find that longest continuous carbon chain. Remember that you do want to sort of check all your options, as it's not always going to necessarily be the straightest one. Again, it can kind of go straight, go up, go over. Remember that when you're counting the longest carbon chain, the only thing you cannot do is backtrack. So you got to go one way and then kind of dead end it. And that will be hopefully whatever your largest one is. Again, I recommend maybe boxing the longest carbon chain. Whatever is not part of that longest carbon chain, those will be your groups. And we talked about alkyl groups. Alkyl groups are, again, basically carbon-based groups. They are based off of those first 10 alkanes. The difference, as we talked about, is that they will be missing a hydrogen. And because they're missing a hydrogen, that gives them a place to really connect in without ending up with too many bonds. So if we had something like a CH3, that is based off of methane, but it is missing one hydrogen. So this is our methyl group. So once you sort of have the longest carbon chain, again, that should be really the base of your name. You want to then, like I said, identify all the different groups. Remember as well, we could have some halogens there, some florals, chlorals, bromos, iodos there. Uh, then the next thing you want to do is, as we talked about, is basically number the longest chain. And the idea of numbering the longest carbon chain in the case of alkanes is the goal is to give the groups here, the groups that are attached, the smallest numbers. So that is sort of the goal here in this type of numbering, is to give those groups the smallest numbering. And again, it could go left to right or right to left. It's whichever way will sort of give you that smallest numbering. And once you have that all arranged, we do go alphabetical for our groups, regardless though of a prefix, if they do have a prefix. So we came across some last time, right? Again, we had a couple of methyl groups in the compound. So we used the prefix di for that. And again, when we name these guys, remember, every time you go between a number and a letter, you do need the dash. Also, if you are going between a letter and a number, you also need a dash. And again, if you got a couple numbers back to back there, you do need commas between them. Any questions on any of that stuff there from last time? We also talked about drawing the structures from the name, which, as I mentioned last time, in my opinion, might be the easier of everything. Remember that if you do have the name given to you and you need to draw it, you should always work backwards in the name and start with just the carbons, add everything else. And again, save the hydrogens for the end. As we've been talking about, we kind of want to use the hydrogens to get carbon to 4 bonds and give it the appropriate number of hydrogens. All right, so take a look at a few more here. Okay, so let's take a look at this one. Again, we're going to look for the longest carbon chain, and in my opinion, I think perhaps just straight across is going to achieve that for us there. There are other options, we go straight across and down, but I think that's only going to give you 4. Here we do have 5. They're all single bonded. So really the base of our name here should be pentane. Now we got some groups here. So we have this guy and this guy. Again, here the hydrogens are not really considered groups per se. And we have a 1-carbon group, so that's going to be a methyl group based off of methane, which has 1 carbon. That's going to be a chlorine, which is going to be a chloral group in this case. So now what we have left is our numbering. And again, in this case, we could go left to right, 1, 2, 3, 4, and 5 carbons. We also obviously could go in the opposite direction there, 1, 2, 3, 4, and 5. It looks like going left to right there gives me a group at 2 and 3. Going in the other direction, this direction, looks like it gives me a group at 3 and 4. And to me, 2 and 3 looks like the smaller number there. So the way we do want a number would be going in this direction. That would put our chloral at carbon number 2. That would put our methyl at carbon number 3 in this case. And that's everything, I think. So alphabetical here, we're going to go C before M. So we got a little 2 chloral, 3 methyl. And then just slap a little pentane at the end there. Should be in business, I hope. Yeah. Any questions on that one there? Okay. Now, let's talk a little bit about cycloalkanes and if we have groups attached, how we go about naming it. Now, if our cycloalkane is what is sometimes referred to as being monosubstituted, which means there's just one group attached, basically. We basically just give the group name and then we just give the cycloalkane name. So clearly in this case here, that right there is our longest carbon chain, which is our cycloalkane. That again has 1, 2, 3, 4, 5, and 6 carbons. That's based off of hexane, but because it is a ring structure, that's going to give us the base of the name as cyclohexane. Here, this is actually our group that's hanging off of it, and that is a 2-carbon group, which is based off of ethane. And since it is a group, it will now become a ethyl group in this particular case, and that will give us ethyl cyclohexane. Now, you do not need to give the number in this particular case because there is only one group attached, and wherever that group is in this ring is always considered carbon number 1 in this particular case. Now, if I had this with, something like that there, maybe we'll go this way here. So in this case, we have a couple of things attached. So we have to do a little bit of work here. Obviously here, our ring structure here is still our largest guy. It's still our 6, so it's still our cyclohexane. Now we do have over here a 1, 2 carbon group, which is our ethyl. And over here, just a lonely line hanging out, which means there's a carbon at the end of that, and that's going to be a methyl group. In this case, though, we actually do need to give some numbers because there is more than one thing attached. So where or how can we go about naming? Well, we would do the same sort of approach, if you will. We could start here and go clockwise, that is 1, 2, 3, 4, 5, and 6. If we did that, that's going to give me a group at 1 and 3. We could start there where I started. Try not to erase the whole thing here. We could start again at this guy and go 1, 2, 3, 4, 5, and 6. And clearly in that case, that's going to give us a 1 and a 5, which is, again, a little bit bigger of a number. So we wouldn't want to go that way. But we also might want to think about another consideration, which is when we're going to number this, we could also start at the ethyl as well, right? And if we start at the ethyl in this case, we could also number one of two ways, and you could probably maybe see that if you go counterclockwise, 1, 2, 3, that's going to do it for you. Again, if you went this way, you're definitely more than 1 and 3, right? If you kind of went in that direction. Now, the reason I might want to number starting with the ethyl versus the methyl in this case is why do you think? Alphabetical, right? So this guy's going to come first in this particular case. So you might want to give them the smaller number since you do have that sort of option. So I'm going to go that way. And this is going to give me 1 ethyl, 3 methyl, again, cyclohexane. So if you have just one thing attached to a cycloalkane, you really just need to name the group in the cycloalkane. If you have a multiple things, you need to think about a couple of things, which way you want a number to give the smallest number. And in this case, it didn't make a difference really in terms of the numbering if I started at the methyl and went to the ethyl or started at the ethyl went to the methyl. But since we could go alphabetical, might as well give that guy maybe the smaller number in the naming. Any questions on that there? Yeah, good. Yes. Yeah. Yeah, so all those alkyl groups, which is a fancy way of saying carbon-based groups, they're all based off of the alkanes. They'll just have one less hydrogen. So when we look at this, that is 1 carbon, 2 carbons. So 2 carbons, it's an alkane, ethane, and that's where that comes from. And then obviously here, there would be just 1 carbon at the end. And again, that would be based off of methane. Yep. Yeah, so most of your groups will come from those alkanes. And we saw a couple of special ones like the isopropyl that we talked about last time. And then probably your other groups will be really the halogens like we were talking about, these guys coming here. Yeah. You would in this case, and that's okay. And again, you probably might want to go the way I did just to give it that priority. But uh, to answer what I think maybe is your question is the numbering and the alphabetical doesn't matter. So you do want to go alphabetical, even if that alphabetical guy that comes first has a larger number than the second one that would come. That's okay. So like in your case, as you just mentioned, if we did kind of go that way we would actually end up with like a 3 ethyl and then a 1 methyl. And that's okay that the numbers kind of go large to small. Again, it's more important to kind of put the groups in alphabetical order. Yeah. You could think these guys, the IUPAC people, 3 guys that make up all the rules or how you name. It's basically just some weird rules. Yeah. Yeah, they do. So that's the International Union of Pure and Applied Chemistry. They're like the guys that come up with all the ways of naming things and like, all these things and all those like type 1 things we talked about, normal naming. Um so I imagine it probably made some sense to them for some reason as to why they did. Yeah, yeah. Yeah, I think it's mainly that, and it's really, really organic naming is all about kind of location, right? Just kind of tell everybody where you can find everything. And to do that, probably the simplest sort of numbering scheme to do that allows it to happen. Other questions? All right, so as we talked about last time, if we want to draw something, just to remind ourselves, let's say we wanted to draw this guy here. Remember, always work backwards and always really just start with the carbons as we've talked about last time. So heptane would tell us that we do need 7 carbons. And again, you could put your 7 carbons up there, maybe leave a little space for some hydrogens or some other things. 1, 2, 3, 4, 5, 6, and 7. That again takes care of that. And then dimethyl means that we do have 2 methyl groups in this compound. In this case, the numbers tell us exactly which carbons they're at. And once again, because you are drawing, you can choose whichever way you want carbon number 1 to be. So again, I can make carbon number 1 on the left. You can make carbon number 1 on the right. It doesn't really matter. In the case of the alkanes, it's really the same molecule. It just turned around if you kind of drew it in the other direction, basically. So I'm going to go over here with this as my carbon number 1, and I'm going to put a carbon because I know methyl is 1 carbon, and carbon number 2 for me would be right there as well. That takes care of all that. And then obviously at 1, I also have a chlorine, and I'm just going to go that way because I'm running out of room. So we'll go that way with that, and that takes care of that. In this case, we're now pretty much just down the hydrogens. And again, remember the key here with this is to get carbon to 4 bonds, and we're going to use hydrogens to do that. So 1 bond coming in here means 3 hydrogens, 2 bonds is 2 hydrogens, 2 bonds, 2 hydrogens, 2 bonds, 2 hydrogens, 2 bonds, 2 hydrogens. I actually got 3 bonds on this guy, so I just need 1. I got 3 bonds on this one. I just need 1. By the way, that is a chlorine, not a carbon, so no hydrogens to that guy. And even if you weren't sure again with your groups, but you were sure of how many carbons it is, you could apply the hydrogens the same way to your alkyl groups. This guy has 1 bond coming in, which means I need 3, 1 bond coming in, and I would need 3. And again, this would be our condensed formula that we just drew here where the hydrogens aren't drawn out. If you want to draw these expanded formula, it'll look just like that, except draw all the hydrogens out with bonds. And obviously we talked about line structure as well, which you can kind of do the same thing. 1, 2, 3, 4, 5, 6, 7. And again, here, do something like that. And then I believe we got 1 there. And I think that's it. In that case, you'll have something that looks something like that. Yeah. Any questions on that one there? All right. So why don't you draw this one? Why don't you draw the formula for 3-bromo, 1-chlorobutane. Why don't you also draw, let's do propyl. Okay, so let's take a look to see how you're doing. So again, we're going to work backwards. So butane tells us it's that'd be 4 carbons, not 6. It's kind of like 4. 1, 2, 3, and 4. That takes care of that. Once again, I'm going to start with my carbon number 1 there on the left. And that means that carbon number 1, I should expect to see a chlorine there. And again, as we talked about last time, it doesn't really matter where you stick the chlorine. You go up to the left, you go down. It doesn't matter in this particular case. And then since I did lock sort of this guy in as carbon number 1, I do need to go from me down to this carbon for carbon number 3 to be our bromine group. And at this point, everything else here is going to be hydrogens. So we got 1 bond needs 3. This guy has 3 bonds, needs 1. 2 bonds needs 2. 2 bonds needs 2. And again, that would be more your condensed formula. Any questions on that one? Line, again, you could just really start with just the carbons, 1, 2, 3, and 4. Again, doesn't matter which side you call number 1, but I'll go this way. And again, you do need to put the Cl at the end of that line. Otherwise, it becomes a methyl group, right? If you don't put the Cl, so you got to put the Cl. Since again, that's going to be my carbon number 1. My carbon number 3 would be right about there. And we would go with the bromine in this particular case. Any questions on that there? All right, working backwards here, that is cyclobutane. That is 4 carbons, but cyclo tells me it's in a ring structure, so I'm just going to draw kind of like a square kind of thing happening there. That's going to take care of that. Propyl is a 3-carbon group, and in this case, it doesn't really matter where you stick it. You can stick it on any corner you like in this particular case, since it's the only thing there. And again, you can do something like that if you like. You could also obviously do those guys and more of a condensed. A condensed, this would be obviously line structure. Condensed would look something like this. Technically speaking, it looks something like this, and a little CH2, CH2, and CH3, something like that, for example. Any questions on that? Okay. All right, couple more names here. What do you got going on here for these guys? Okay, let's take a look. We'll start with A, and to me, it looks like just straight across is going to get us our longest carbon chain there. And if we count it up there, I'll put little dots there. 1, 2, 3, 4, and 5. So that means the base of our name here is going to be pentane, as it's all single bonded. In this case, we have really only one group attached, which is our chloral group here. And you could probably just looking at see probably the best way to number would be starting at this end, as that's going to give us obviously a 2 here for the chlorine. Obviously, if we started at the other end, we would end up with a 4, which is obviously a larger number. So that's going to be a 2-chloral pentane in this case. Questions on that one there? All right. I think just looking at it, I think this is still going to be our longest carbon chain of 5. Other options would be 1, 2, 3, 4, 5. You could kind of go that way and get you 5. Again, you could get it a couple other ways. I think 1, 2, 3, 4. 1, 2, 3, 4. So I think that's probably going to be our best. So I'm going to go that way. So again, here we're going to get a pentane as the base of our name. We have a line hanging out there and a line hanging out there. That is a methyl group when nothing else is written for each of them. That is 2 methyl groups in the same compound, so that's a little dimethyl action happening, right? And lastly, we need to give our location. And I think if we go left to right here, 1, 2, 3, 4, 5, that's going to give us a group at 2 and 3, which looks better than if I went this way. 1, 2, 3, 4, 5, which would be 3 and 4, obviously, which would be a larger way. So we would want a number in this direction. And putting all that together there, 2 comma 3 dash dimethyl pentane. Any questions on those there? All right, so now that we talked about naming and drawing them, a few more properties here of alkanes. Alkanes are solid alkanes, make up like those waxy coatings that you see on our fruit there. Methane, ethane, propane, butane. Again, a lot of those are very much gases at normal conditions. Again, because as we talked about, they're held together by that kind of weak dispersion forces because they're pretty much non-polar, right? So it's very easy for them to be in the gas phase. It's also very easy for them, as we talked about, to go into the gas phase, even if they're in the liquid phase. They're again very volatile. And again, what that means is they're basically be in the liquid phase 1 second, open the lid, and now they're going to jump into the gas phase pretty simply along the way. Again, as I talked about, a lot of them are also very flammable, which is not great, again, if you're using a Bunsen burner near any of that, which is probably not usually recommended as well. Alkanes with 9 to 17 carbons are liquids with higher boiling points, and that's like stuff you find in motor oil, mineral oil, jet fuel. Decane has 10 carbons. Alkanes with 18 or more are more like your waxes and parafilms. And again, 25 or more, you get into some like Vaseline, petroleum type jelly type of things. These are things that are non-polar. Remember though, if you are comparing, for example, although these guys pretty much will have your lowest melting points and boiling points, that if you are comparing one alkane to another, the strength of dispersion forces does increase with molar mass. So if you have somebody that has a longer sort of carbon chain like this, it would actually have probably a higher melting point than something with a smaller carbon chain. They're both will be relatively low. But again, the strength of those dispersion forces increases with size and molar mass. They are typically nonpolar, insoluble in water. They're also usually less dense than water. That is always, for the most part, where you find the organic layer. It is usually the top layer. If you are kind of mixing it with like a water layer or an aqueous layer, that's the bottom layer when they kind of mix out. As you have seen, perhaps oil spills in the ocean, right? The oil just kind of floats down the river there, or the water. Now, alkanes do go through a couple of different types of reactions we're going to kind of talk about. One of which we've talked about previously when we talked about reactions. They, much like most organic compounds, will go through combustion reactions. So we could have our organic alkane, O2, CO2, and water. And also flame is typically what we see when we go through a combustion reaction here. That is, again, what happens when you light your Bunsen burner. Pretty much you get the flame going on there with a spark. So that is a reaction that we've seen before. Here's butane going through the same thing, O2, CO2, and water. And again, heat and energy is usually given off as a result of that. Now, a couple other reactions that alkanes undergo are another type of reaction is what is referred to sometimes as a substitution reaction. And basically, the substitution reaction, what happens is somebody comes on and somebody goes off. So they basically sub out for each other. And in the case of alkanes, what typically will happen, for example, is if you had some type of alkane and you added, say, something like Br2 to it, which is basically this, right? Br2. And maybe a little light and heat helping in this. So what happens in this case is we get a substitution, which is one thing comes off, the other one comes on. In this case of an alkane, it's always going to be a hydrogen. And when we look at all these hydrogens, they are all what are referred to as being equivalent hydrogens. They're basically the same hydrogen. They're all, in this case, primary hydrogens, right, off of primary carbons in this case. So really, in this case, we sometimes draw what is referred to as the monosubstituted product. And basically what that means, for example, is this guy will come on and this guy will come off, basically. And really, you could do it for any of the hydrogens that are sitting there. It doesn't really matter which one you pick, but one will come on and one will come off. And one of the first things you should learn in organic chemistry, especially for our class, is things don't do all kinds of funky, crazy things. Pretty much just one thing changes. And what changes typically when we have a reaction is where any of those kind of functional groups is really where things happen. So as you can see, everything up until this point is exactly the same. Nothing changes. Everything is identical. The good news on that is in this class, you pretty much have almost all your drawing that you need to draw in the problem itself. So you actually have most of the answer. The difference is we're then just going to add a BR there at the end. And we did take a H off, and there's one more BR. They actually will come together and make a little HBr in this case and make that guy here. Again, you could do it for any hydrogen on there. It's all the same. Because what would I call this, by the way? This is bromoethane, yeah. And so would it be if I did that hydrogen or that hydrogen or that hydrogen, they would all be basically the same thing, basically, yeah. Now, you could also do this, for example, on a, dare I say, cycloalkane, right? Now, again, although not drawn, this guy, for example, does have a couple of hydrogens hanging out there. And if you did a little of this action here, again, Cl2, this guy's going to come off. One of these guys is going to come on in his place, and you'll end up with one of those guys and some HCl. So this is what is referred to as a substitution reaction. One guy comes on and one guy comes off. In the case of alkanes, a hydrogen comes off, and you throw one of those guys on there in its place, basically. It's way more complicated than that, but that's what happens, basically, to get it there. Any questions on alkanes and reactions? So combustion reaction, sort of a substitution reaction. Any questions on that? Okay. Then let's talk about some more organic guys here, and we're going to talk about then The next couple groups of organic compounds, alkenes and alkynes, they have functional groups for each of these. Remember, the functional group is the part of the molecule that makes it that type of organic compound. For alkenes, you need a double bond. Yeah. And for alkynes, you need a triple bond happening there. Yeah. So those are the functional groups for each of those. Alkenes, much like alkanes and alkynes, they are related to each other. So we saw earlier CnH2n plus 2 is our general formula for an alkane. Now, when we put a double bond on, and as we talked about, I think last time as well, every time you throw up another bond there, you do have to lose 2 hydrogens, one from each carbon. So when you get to an alkene, which has a double bond, it has a general formula CnH2n. Again, it's not going to have those extra 2 hydrogens because we had to put a double bond on it. And if you go to an alkyne, that's a triple bond. And that's going to be CnH2n minus 2. So you're going to lose 2 more hydrogens. What do I mean by that? I don't know. Let's take a look. Let's see. This is our alkane, which is 2 carbons. That is ethane, ANE. If I want to make a double bond between those two, I got to sacrifice 1 hydrogen at each carbon that's going to make the double bond. Otherwise, I have too many bonds there. This, believe it or not, is not ethane, but ENE. This is ethene, ENE, just like the group name there. And I won't draw the triple bond because it's right here. And when we put on our triple bond, we have to take off 2 more hydrogens. And as you might guess, this guy's name is ethine, YNE, like the functional group there. So they are all still based off of the first 10 alkanes. We just kind of changed the back part of the name there, ENE, because we have a double bond. YNE, we have a triple bond. Again, kind of just they go back to those alkane names. Question on that. Again, you can see we do have to sacrifice, for example, 2 hydrogens to make our double bond. We have to sacrifice 2 more hydrogens to make our triple bond, yeah, as we go that way. So again, every time you put on a bond, 2 hydrogens got to go to make room for it, basically. Yeah. Any questions on that there? Yeah. There's not, because in order to make a double bond or a triple bond, you need 2 carbons. So the simplest alkene or alkyne you could have is really 2 carbons. Yep. Other questions? So as I mentioned, they are hydrocarbons. These are what are referred to as being unsaturated hydrocarbons. If you remember, saturated hydrocarbons is what we find with alkanes. They have the maximum number of hydrogens that they should have because they're all single bonded. So as we just talked about, every time we put on a bond, we lose a couple of hydrogens. So these are what is referred to as being unsaturated. They have at least a double bond or a triple bond, which means by that definition, they don't have the maximum number of hydrogens that they could have based on the carbons that are present. All right. So identifying alkenes, again, that double bond is definitely the identification. It also, by the way, does change the bond angle of the molecule. Like we saw with alkanes, which have a tetrahedral geometry. Here with our alkene, we have 1 electron pair, 2 electron pairs, and 3 electron pairs. And we also have 1, 2, and 3 bonds. That is our trigonal planar or our triangular, which has a bond angle more of 120. And again, you could kind of see the triangle happening there, basically. Same thing on the guy on the other side. He's got the same geometry. So unlike that sort of zigzag type of shape, here we have a bond that's occurring. And ethene, for example, is important plant hormone, and alkynes have a triple bond. And once again, that triple bond also changes the geometry, because now with our triple bond here, maybe I'll draw it a little bit bigger up here. We look at this carbon, it has 1 electron pair and 2 electron pairs. Remember, when you're doing geometry, right? Everybody counts as 1, right? Double bonds, triple bonds, single bonds, everybody's a 1. That's 2 electron pairs and 2 bonds. And that is actually linear in geometry. That's 180 degrees is the bond angle that happens here. So believe it or not, sometimes when these people draw, for example, line structures, they incorporate that. And they do something like this, perhaps, right? And again, this would be your triple bond here, little flat, not so zigzaggy. I'm okay if you still zigzag it. I don't care. But sometimes you'll see it like that. So if you want to do a double bond like that, that's all good. Heck, if you want to do a triple bond like that without doing the geometry, I'm good with it. It's all good. But you will see it sometimes kind of flattened out in books and stuff like that because of the different geometry that occurs in this particular case. By the way, when we do something like this, right, this is 1 carbon, right? 2 carbons, 3 carbons, 4 carbons, and 5 carbons. I will say that sometimes when it is drawn like this, people miss the carbon. There is a carbon here, and there is a carbon here on the opposite sides of the triple bond. So sometimes when it's drawn in that kind of straightish type of format, when people are counting carbons, they just kind of, I think their eye just kind of skips over, the carbons that are there, and they kind of look at the ones to the right and left there. But there are carbons there. So just be careful when you're counting, especially if it's line structure and it's a triple bond and they did kind of flatten it out. Sometimes people miscount the number of carbons that are there and they kind of go over it. Now, how do we go about naming it? It's a good idea. Let's talk a little bit about naming these guys. When we name these guys, we still do the longest carbon chain. Now, the important part of the longest carbon chain, when you have a double bond or a triple bond, is it needs to contain the double bond or triple bond. So you can't go around the double bond or triple bond. The longest carbon chain does need to have the double bond or triple bond in it. That's going to give you the base of your name, except obviously you're going to adjust it as either ENE or YNE, depending on whether you have a double bond or a triple bond present. Now, also a little bit different than alkanes is when you have a double bond or triple bond, it actually does take the priority, and it takes the priority in terms of numbering. So before we were numbering to give all the groups the smallest numbers. Here, when we have a double bond or a triple bond, we need a number to give the double bond or the triple bond the smallest number. So it is the double bond or triple bond that should have the smallest number. And once you lock that into place, you do have to number every other group that's there based on that numbering that you did. The rest of it really is the same. We still, we still give all the groups in alphabetical order. We still give their locations. One other thing that's also a little bit different when we have a double bond or a triple bond is you do have to, at some point, usually around 4 carbons, you do have to give the location of where the double bond is or the triple bond is located. So you do have to kind of give that location with a number as to where it is. Again, you want to give it the smallest. Now, why do you not have to do it with this guy here, which obviously is ethene? All right. Is there any other location where I could put the double bond? There's not, right? So it could only go in that one spot. When you have 3 carbons, you're either going to put it on the left-hand side, right, or the right-hand side, which will give you basically the same thing. So when you get to about 4 carbons or more, usually that's when you do have to give the location of where that thing is. So let's start with, though, is the first one an alkene or an alkyne? First one is an alkene, and that is because it has obviously a double bond, right? So double bond is an alkene. This guy is a alkyne as it has a triple bond. So while we're at it, why don't you give it a shot there and see what you come up with these names. So in each of these cases, we definitely have more than 4 carbons. So you need to give the location of the double bond or triple bond. You also need to, again, give those guys the smallest numbering. So give it a go and we'll talk about how we get to those names. All right, let's see how we're doing. We'll take a look at the first one. So same thing. We want the longest carbon chain. Since there is a double bond, it needs to be included. In this case, that's like everything there, basically. So we just need to count up some carbons. We got a 1, 2, 3, 4, 5, 6, 7, and 8. It has a double bond, so that's an ENE. So instead of octane, it's going to become octene. I do need to give the location of where the double bond's located because definitely there's more than one option as to where you could do that. And you could probably see that if you go left to right here, 1, 2, and 3, that definitely is a smaller number than if you went in the other direction, 1, 2, 3, 4, and 5. Yeah. And we would kind of count where it starts depending on which direction you're going. So this would be the way we want to go. So how we incorporate that into the name is this is 3-octene. The 3 is the location where the double bond's at in terms of that. No, you would not. So yeah, so you would pick whichever direction you want to number it, and whichever direction is to the smallest number is where it first starts, basically in that direction. Yeah, yeah. Other questions? Now, if we take a looky over here at this guy, scary. I think I think if we go this way, we're actually going to hit the most. Let's see. So again, as I was mentioning before, that is a carbon there, by the way. The next carbon is actually right about there. Yes. Again, at the other end of the triple bond, oftentimes missed. People just kind of come over here and stuff like that. So that's what I was saying a second ago. So that is 1, 2, 3, 4, 5, 6, 7, and 8. Now, your other option, which I don't think is going to get us to 8, but you could have done 1, 2, 3, 4, 5, 6, and 7. So that clearly didn't get us to 8. The one thing that you cannot do, though, is you cannot do this 1, 2, 3, 4, 5, 6, 7, and 8. I can't do that because what did I just do? I avoided the triple bond, right? So again, the double bond or the triple bond needs to be part of the longest carbon chain, so you can't go around it. Even if you may see something that looks like it, maybe it has more, it's got to include the double bond or triple bond if it's present. Question on that there. Okay, so now that I put dots everywhere, let's undot some of this maybe. All right, so clearly 8 is our winner here. We do have a triple bond happening here. So this is going to be a little octine action. We do need to give the location of the triple bond, which I think is pretty straightforward. It's got to be right about here. 1 looks like a winner there. So that's a 1-octine. Because I have to lock in the numbering based on the triple bond, I do have to lock it in for everything else that's attached in this case. And that means here's our group that's attached, right? And this is a 1, 2, and 3 carbon group. So that's going to be a propyl group. And that is at carbon number 4. I'll try to squeeze it in here. 4 propyl 1-octine. Yeah. Any question on that name there? So again, that's sort of what I was talking about a second ago about the triple bonds. Sometimes people just skip the actual carbons. It kind of blends in, and they kind of go like here to here without hitting that guy in the middle. Any questions on those there? So as we just talked about, the IUPAC name is based off of the alkanes. We're just going to do those slight changes. There are also cycloalkenes as well. So this here, all single bonded, is 6 carbons, cyclohexane. Now, if I lay myself up a double bond, just one, that now is cyclohexene, as it has a double bond happening in this case. So we would name it the same way. All right, so why don't you try the names here and see what you come up with? Why don't you also draw something? I'll make something up. Let's see. Let's go with let's go 4-chloral 2-hexene. We'll find out shortly if that works. Okay, so let's take a look. Again, I'll start here. Looks like 5, I think. 1, 2, 3, 4, and 5. Again, that does encompass the double bond. You could also get it by going 1, 2, 3, 4, and go down if you like as well, which is 5. So I'm just going to take kind of the straightest one here. So 5 with a double bond is going to get me to pentene. Here I do need to give the location of that double bond. And again, to me, just looking at it going in this direction will give that double bond the smaller number. Obviously, going in the other direction, I'm going to hit like a 3, I think. So that's going to be a 2-pentene. Because, again, I had to lock in my numbering for the groups that are attached has to be numbered the same way. And that means that my one line here, which is a methyl group, would then has to be at carbon number 4 because I kind of locked it in. And that's going to give me a 4 methyl 2-pentene. Yeah. Any questions on that one there? All right. Triple bond going on there. So straight across, I think 1, 2, 3. Remember 4, 5, and 6. Yes, again, you don't want to kind of skip over the triple bond there. So what did I say? 6. 6 with a triple bond hexine. Do you need to give the location? You could probably see going in this direction should work pretty good. And that's going to give me a 2-hexine, and that's it. There's nothing else attached in this particular case. Any questions on that one there? All right, so we're going to draw. We're going to go backwards. So hexene, ENE, that is 6 carbons. Yeah. I'll go up here, I think. 1, 2, 3, 4, 5, and 6. So ENE means there's a double bond, and that's at carbon number 2. So once again, since you're drawing, you can go whichever way you like. I'm going to go this way, making this my carbon number 2 right there, right? And that means since this is my carbon number 2, my carbon number 4 would be right about there. And I would need a chlorine. Again, you could go one up if you wanted to. Yeah. Yeah. If you drew the line structure, it would probably be fine if I just said draw it. Yeah. So if it said to draw the condensed structure, that's technically what I'm drawing right now. If it said to draw the line structure, then you should draw it like on the left. In this case, yeah. And at this point, we're out of names. So hydrogens to fill out the 4. So 3, 2, 1, 1, 1, and 2. And to answer your question, obviously, if you drew it line structure, you would again start with your 6 carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and 6. And again, you would put your double bond here, perhaps at carbon number 2. And 3, 4 would be a chlorine, something like that. Yeah, something in that ballpark. Question on that there. Cyclopropene. Propane is 3 carbons. Cyclo means it's a ringish type of triangle. And ENE means there's a double bond somewhere in there. So pick a side, whatever side. Doesn't really matter because if you turn it around, it's all on the same side, basically. Yeah. Any questions on any of those there? And again, if you wanted condensed on that, it would be something like this. Like that, yeah. All right. All right, so naming cycloalkenes is a little different. Now, because there is a double bond in the ring, if you have a group attached, one group, you do need to give that group a number in this case, relative to where the double bond's located. Now, the importance of doing this is you do have to make sure that when you go to number, you follow one important rule, which is you do have to number through the bond. You cannot go away from the bond. So what I mean by that, for example, here is we'll take this guy here and we'll lay us up maybe a double bond there. And then we got like a methyl group, okay? So we do need to give the location of this methyl group, and we do want the smallest number, and you may be tempted like, can I just go 1 and 2? And the answer is no. You do have to actually number through the double bond. So that gives you really, in this case, 2 options that you can do. And those 2 options are you could start at this double bond here and go 1, 2, 3, 4, and 5. Obviously, that would put our methyl group at number 5. Your other option would be to start number 1 at this side of the double bond and go counterclockwise. 1, 2, that takes us through the bond, and now to 3 here. And so we would want to go in that direction. It gives us obviously the smaller number. So that's a really important detail when you're kind of numbering and naming a cycloalkene. You do have to number through the bond. So you have to go, one end of the double bond through it to the other end and go around, or start at the other end and go through it and go around. So that is how we get to this name here of 3-methyl. And again, this would be cyclopentene, right? ENE. You do not need to give the location of where the double bond is located. It's always assumed to be carbon number 1 in there. So you don't have to give the location, but you do have to use it to number anybody else that may be there. Obviously, as well, if we had, another methyl group on there, right, we would do the same thing. We have to get the location of both of them. And again, in this case, we may want to go in this direction, which would give us a 3 and a 4. Obviously, if we go in this way, 1, 2, 3, 4, and 5, we're going to get longer numbers or bigger numbers going in that direction, which we don't want to do. So again, we would also do something like our dimethyl in this case was naming it as well, since we have 2 methyl groups. So that would then turn into something like 3,4-dimethyl cyclopentene. And again, so if you have multiple groups, you got to number it, still numbering through the double bond. Any questions on that there? All right, so why don't you give it a go, see what you end up with here for each of these. There's our longest carbon chain. So we got 6 carbons on that. We also do have a double bond. So that's going to put it as cyclohexene, ENE in this case, because of the double bond. We, again, do not need to give any location of this double bond because, again, wherever it's at should be carbon number 1. And there's obviously nothing else attached there, so there's nothing else we need to do. Any questions on that one there? Coming here, that right there should be our longest chain. That's going to give us a base here of cyclopentene, ENE, as it has a double bond. Here we do have a methyl group there. And we got one more methyl group for good measure. So that's going to be a dimethyl happening. We do need to give the location of where that bond is, or those bonds are. Remember, again, we need to go through the double bond. So we could start here, perhaps. We'll go 1, 2, and 3, obviously, in that direction. If we went in the other direction, as you can probably see, you're going to get a much larger number there, I think, than 3. If you went in this direction, 1, 2, 3, 4, and 5, obviously that is much larger. So we would want a number going this way. And again, we do need to give both numbers twice here. And that's going to be a 3, 3, again, for both of the locations, dash dimethyl, try to squeeze it in here, cyclopentene. Yeah. Any questions on that one there? Yes. You don't, no. You don't need a dash between the di and the methyl if that's what you're asking. Yeah, no. Yeah, so the dash is really used between a number and a letter. Or if you're going the opposite way, starting with a letter to a number, that's where you use the dash. Yeah. And the comma is only used back-to-back numbers, basically. Yeah, so just back-to-back numbers. Yeah. Probably not. Technically speaking, you shouldn't have a space, but probably not in reality right now. I do that sometimes, like I put a little space and try to squeeze it in there. Then sometimes I'm like squishing everything together. All right, other questions on that? All right, those are hands. So let's talk a little about isomers here. And these are cis or trans isomers, and cis or trans isomers sort of happen when we get a double bond happening. And the reason for that is, as we talked a little bit about, I think last time, when we have an alkane and really a single bond, there is kind of free rotation around that single bond. You could just like spin it around and everything's good. When you sort of lock in a double bond, or even to another extent, a triple bond, but we'll talk about double bonds here. When you lock in the double bond, you actually lose that ability to just freely rotate groups around in like a circle, basically. So this basically will lock groups in terms of three-dimensional space in certain arrangements of where they are in relationship to our double bond. And there's two relationships that we talk about, which is cis or trans isomers. And what cis basically means is the same side of the double bond, and trans means opposite sides of the double bond. Now, what we're talking about is groups that are located either on the same side of the double bond or on opposite sides of double bonds. In the case of cis or trans isomers, we can consider sort of hydrogens as groups when we're kind of looking at cis and trans, even though normally we don't kind of think of them as groups. So how do you know if a cis or trans is really even possible? And there's two things that you sort of have to look at to determine whether or not it's even possible to have a cis or trans isomer. So first off, it always involves the double bond. So that's like where you should focus in on if you're looking just for cis or trans. And when we look at the double bond, there's a carbon on either end of it. And we're looking at really what groups are attached to each of those carbons. So the first thing that you need to have in order for it to possibly even be a cis or trans isomer is you need to have different groups on each of those carbons. So the same carbon cannot have the same group on it. Cannot have two hydrogens on it, cannot have two bromines on it, cannot have the same group on the same carbon. If you see that, so for example, if you saw something like this, that eliminates the possibility of cis or trans even happening because of that. Now, that also means that on this carbon on the right, you also need different groups attached to it. So that's the first thing. You got to have different groups on each of the carbons in the double bond. The second thing you need is a group on each of those carbons that are the same. So in this case, right, we have an A and an A. Those are the same on opposite carbons in the double bond. And even in this case, we could look at B and B are also, right, the same. And in this case, they're on the same side or opposite sides of the double bond. Yeah, either one. You could actually look at either one in this case. So what I just drew here is essentially the cis isomer. You could have something like this, where you got something going on like this, and this would now be trans. And again, you could look at the A's if you want. You could also look at the B's, and they're on opposite sides of the double bond, which would make a trans. Yes, sir. So it's a little bit different. Resonance structure has to do with really moving the double bond around. Here, the double bond actually, what it does is it locks everybody else on those carbons into place, and they can't actually move around. So that's why we get two distinct sort of structures that occur. Yeah. Yeah, they are definitely related to each other, and they are isomers. And right, remember, isomers are basically the same molecular formula, just sort of different connectivity. And in this case, that's what we got going on, really, in this case. Now, again, if you don't have a common group on either side, you cannot have a cis or trans. So here, if we look at this one, you want to focus on the double bond. Here I see a chlorine and a hydrogen. Those are different groups. Here I see a chlorine and a hydrogen. Those are different groups. And now on opposite carbons, I see chlorines that are the same, and they're on the same side. So that would be our cis isomer. Here again, we want to focus on the double bond. And once again, I have a different group, different group, different group, different group, similar group on opposite guys, and they're on opposite locations. And again, that would be your trans in this case. Any questions on that there? All right. So cis and trans have different physical and chemical properties because, again, like I said, those kind of double bonds lock everybody spatially into place, and it does give them some different properties because of that. So this is cis to butene. Let's just say we wanted to draw cis to butene, right? So how would we draw it? How would I recommend drawing it? Well, if you had to draw something where you needed to show cis or trans, I personally would probably not draw the cis or trans right out of the gate. I would just draw this like normal. And so like normal, butene, it tells me it's a double bond and there's 4 carbons. So I would do my 4 carbons. I would put my double bond at carbon number 2. And in this case, I might add some hydrogens here for sure. And when I get over here, I might actually kind of draw some hydrogens here so I could see them. And what that's going to let you kind of visualize is the 4 groups that we kind of need to see around that double bond. So how would I redraw this to give me my cis or even my trans? What I would do is, again, I would start here with just the double bond now that I got really the structure going on. And once I have the structure here, the basic structure of that double bond, I can now see my 1 group, 2 groups, 3 groups, and 4 groups that are attached. And now if I want cis, I can see methyl groups right on each side there are the same. So I could choose and just do my methyl groups up, right? Which now definitely puts it in the cis sort of transformation there, or conformation. And that's just an easier way to do it than trying to draw it maybe right out of the box. You could also, obviously, if you wanted the trans in this case, you could start with your double bond You go one methyl down, you go one methyl up, and you could also throw some hydrogens in there as well. And again, now you have it in the trans. So if you have to draw any of these, where you come across where you have to kind of draw it with the cis or the trans, try to draw it straight, isolate the double bond, figure out the groups that are attached, and then just redraw it sort of the way that you need it. Any questions on that there? And here is in line structure. As you can see, again, our bromines here are on the same side of the double bond, which is right there. And our bromines on this guy are on opposite sides of the double bond there, which gives us our trans. How do we incorporate it into the name? We basically just add cis or trans to the beginning of it, and we name it just like normal and stuff like that. All right, so for each of these, determine if they're cis or trans, and why don't you also name them all as well? Okay, so let's take a look at the first one here. So again, I would recommend if you're trying to figure out cis or trans, I would maybe isolate the double bond. And again, we do see some chlorines and we do see some methyls, right? And this can be a cis or trans, right? Because we have different groups on each carbon. We also have some similar groups, and this would be cis or trans in this case. This would be cis, as you can look at either one. The chlorines on the same side of the double bond, or the CH3s are on the same side of the double bond. So that would be cis. Let's just go through and talk about cis or trans first, and then we'll name. Coming here again, looking at our double bond, we have a different group, different group, different group, different groups is good. Similar group, or again, you could also look at the methyls if you like. And in that case, they are on opposite sides of the double bond. So this would be a trans, right? Once again, looking at the double bond, we have different and different, different and different, similar and similar. And those are on opposite sides. So this would be trans. How about a couple of my additions over here? What do we think on the top one? Cis or trans? Or neither? What do you think? Well, my double bond is here, yeah? By the way, there's a hydrogen there, right? So we have this group, which is different than this group, right? We have this group, which is obviously different than the hydrogen. The group that's actually the same is the methyl group on each side, right? And that would mean that it would be a cis in this case, yeah. How about this one? This would be cis, trans, neither. Cis, neither. It would actually be neither because this group and this group are the same. So that eliminates the possibility of cis or trans. That is neither, yeah. Not the three. So when you look at the carbons in the double bond, on each of those carbons, they have to have different groups attached. So because this one has a methyl group and a methyl group attached, that automatically eliminates the possibility of cis or trans. Yeah. So if you look at all the other ones, this group on the carbon on the left and this group on the left are different. So that's good. And this group are different on the carbon on the right. So that's good. So, but if you hit one where one of the carbons in the double bond have the same two groups attached to it, that means that you cannot have cis or trans. So that's good. Yeah. Question on that. All right. Well, now that I got rid of all this stuff here, let me do a little erasing here. All right, let's talk a little bit about names here. Why not? All right. Longest carbon chain there in the first one is how many? Not everybody at once, but what do you think? Longest carbon chain is 4. Did you see it? It is 1, 2, 3, and 4. Yeah. So sometimes when people have it drawn in cis and trans, they're so focused on the double bond everybody only has 2 carbons. Yeah, and that's all they focus in on. So you got to still do the same things we did before. Longest carbon chain that has a double bond in it. In this case, that is 4, which means this guy is butene, right? And a little butene in this case. And in this particular case, the double bond would be at carbon number 2. Don't really matter which way you go, actually, in this case, right? So that's going to be carbon number 2. And we really only have 2 chlorines attached here in terms of our naming. Again, those methyl groups that we kind of looked at as methyl groups with our cis or trans are actually part of the longest chain. So they're actually not groups when we go name it. And that's going to be we go 1, 2, 2, 3, I think. 2, 3 dichloral. I'll dash underneath 2 butene. And obviously we would throw a cis in front of that. Yeah. So that would be a cis 2, 3 dichloral 2 butene. Question on that one there. Longest carbon chain on this one then would be also 4. Yeah. So again, that would be it as well. That's going to give us our 2 butene again on all of these probably. And again, in this case, we have some bromines. So that's a dibromal. And again, I would say a 2 and a 3 probably will do us on that. So that's going to be a 2, 3 dibromal, 2 butene. And obviously we would put a trans in front of it as well. Same thing on this guy coming through this way, actually. Is there any other groups attached in terms of naming? There's actually not. The hydrogen, again, we want to name as a group for naming. So this actually is just trans 2 butene in this case. Yeah. Any questions on those there? The one I made up, I have no idea. Let's see. 1, 2, 3, 4, 5. And I'm thinking 1, 2. And that'll be 3 there. So I'm thinking like a 3 methyl. I counted 5, I think, right? So 2 pentene. And we went with cis, I think, right? So cis in that case. Any questions on naming or identifying cis or trans? So that's the really key thing. Double bond carbons need to have different groups on each one and a similar group on opposite ones, yeah, in order for it to be possible. Any questions on that there? Okay. All right, so let's talk a little bit about reactions that alkenes undergo. And they do undergo addition reactions. And addition reactions are a little bit different than substitution reactions. We are going to actually add things in, and as opposed to substitution where somebody comes off, somebody comes in. So in this case, we're going to add, and pretty much all reactions occur at the functional group, basically, our functional group site. And for alkenes, that is our double bond, basically, right? So when we have a double bond, what we're going to do, for example, is we could add what is sometimes referred to as a symmetrical addition when you add something like hydrogen. Hydrogen is basically 2 hydrogens, right? Is basically what you're adding. So as we maybe talked about previously, I cannot just throw those hydrogens on the guy on the left, right? Because each of the carbons will end up with too many bonds, right? So much like when we put a bond on, we take off hydrogens. We actually need to remove a bond to make room for what's coming in. And basically what you do in this case is always in this case, your double bond becomes a single bond. And that's going to allow everybody to have enough room. Absolutely, positively, 100%, nothing else changes. So like I said earlier, this picture that you started with should pretty much be the picture you end with. The only difference here is we're going to make some room for things. So we're just going to copy it exactly the same, except I'm going to make that double bond into a single bond. And I'm going to keep all my hydrogens that were there before. And how the addition works is basically the way we remove hydrogens when we make a bond is we take a hydrogen from each carbon. So when they come in, one hydrogen goes to one carbon, the other goes to the other carbon. And basically we slap a hydrogen there, we put a hydrogen there. That is it. We go from an alkene to a single bonded alkane, basically. Yeah. This is what we like to call partially hydrogenated, right? This is a hydrogenation reaction, right? It's how you get like margarine and stuff like that. Yeah, all that good stuff. Hence, I'm assuming the picture of the margarine there. So this is what is referred to as a hydrogenation reaction because we're adding hydrogen. By the way, you could do this with halogen as well. Works the same way. Add a little Br2. Once again, we're going to make this double bond into a single bond, and nothing else is going to change. We'll still have all the hydrogens we started with. Everything's exactly the same. Now all we have to do is throw a bromine on each of the carbons, and we are done. And there you go. You put a bromine there, you put a bromine there, and you are good to go. So in this type of what is referred to as a symmetrical addition reaction, you basically get rid of the double bond, make it a single bond. The two things that you're going to add in, one goes to one carbon, the other goes to the other carbon. It is called sometimes a symmetrical addition because you ideally should not mess it up because it doesn't matter which one gets which bromine. They're all the same, right? So because you're adding two of the same thing, ideally one goes to one goes to the other. It doesn't really matter in that case. Any questions on that there? By the way, it doesn't matter how many carbons you got either. Everything stays the same. So for example, if I had something like this, group is the double bond. That is the only thing. And by the way, that is pretty much the only place it's going to change. So once again, you pretty much have your answer staring at you. You just need to copy what it looks like. Again, nothing fancy happens. No rings start to form, nothing else crazy happens. So all I'm going to frankly do is just copy this thing exactly the way it is. I'm just going to turn my double bond into a single bond, basically. So I'm just going to go a little bit of that there. I'm going to go here. I'm going to go next. I'm going to go here. I'm going to keep the hydrogen again, single bonding this up at this point. We're going to go there, still have those hydrogens. Now, what I essentially did by getting rid of the double bond is I made room for basically these two guys to come in. And again, because they are the same thing, it really doesn't matter which one you put where. They cannot go on the same carbon, obviously. They has to go on opposite carbons. So again, you can't necessarily hopefully mess that up. You're just going to kind of slap in some bromines and that is it. Yeah. So sometimes people get a little crazy when they start drawing things. Yeah. And I would highly recommend you just draw what's there and just change the one little part of it, and you'll be in much better shape, I imagine, at the end of the problem. Any questions on that? So these are what are called symmetrical additions. When we add H2, it's specifically called hydrogenation reaction because we are adding hydrogens. When we do that, we basically get rid of double bonds, and that's again, like I was saying earlier, what it means when they say this is partially hydrogenated. They basically added some hydrogen and got rid of some double bonds. What that does is it actually changes the property of something from more like an oil to, for example, more like a solid margarine or something like that. And that's basically how you get like margarine and stuff like that. And it usually will involve some type of catalyst. So you'll sometimes see up on top of the arrow something like platinum, nickel, something written there. It really has no effect for our purposes on anything other than that's usually used to speed up the reaction and have it occur. Now, there's also unsymmetrical addition reactions, and I'm thinking I can do it right here. And there's one that's known as a hydration reaction. Hydration reaction means we're going to add basically water into this. So when we do that, if we take a alkene here, do something like this, that, and do that. And let's say we add water. And when we add water, you could think of water in this case as H and OH. That's essentially the two parts of water that's going to be added in. Now, this is what is referred to as an unsymmetrical addition. And you're basically adding two different things. So there are a couple rules that you're supposed to follow when you're doing this type of addition. But first off, nothing else really changes other than what we just talked about. I'm going to start by just recopying this thing, and I'm going to again make room for what's coming in by turning it into a single bond. So I'm going to recopy this guy exactly the way it is. All I'm going to do again is turn my double bond into a single bond. I now have basically room on those last two carbons for the H and the OH. There is actually a rule that you should follow, and it says that the H will actually end up at the carbon that had the most hydrogens to start with. This is what is called Markovnikov's rule. I won't spell that, but that's what the Markovnikov's rule. And basically what that means is, how do we know what we're talking about here? We're going to go back to basically what I box, right? And when I box those two carbons, when I look at this carbon on the right, how many hydrogens are directly attached to it? 2. So it started with 2 hydrogens. This carbon on the left has how many hydrogens directly attached to it? 1. Yeah, it's got the guy up on top, right? 1 hydrogen. So the carbon in this double bond that actually started with the most hydrogen is the one on the right, and that is where the hydrogen should actually end up. And that means that the OH will end up on the other one, basically. So basically here, we will throw our hydrogen there from our water, and our OH will go to the other spot, which would be in this case right about there. This is what it's referred to when you do this Markovnikov addition as the major product. And usually when you draw these things, you want to draw the major product. What would the minor product be? It's basically the opposite. Just switch those guys around, put the hydrogen to the left and the OH to the right, and I'll give you the minor product, which usually you don't really want to draw. You usually want to kind of go for the major product in this case. By the way, I went from an alkene in this case, added water through a hydration reaction, and ended up with an OH group, which is an alcohol. Yeah, so this is the way that we could form an alcohol by adding water to an alkene. Just so you know, in terms of naming this, also goes back to our alkanes. That's how many carbons on that guy on the right? That's 3, which is based off of propane. Alcohols end in OL. So this is what is known as propanol, OL for the alcohol. And much like the double bond or triple bond, you do have to give the location of where the OH is, about 3 or more carbons. That OH is at what carbon? Number 2, no matter which way you go, right? It gets you number 2. And that would mean that this guy here is what is known as 2-propanol, which is an alcohol in this case, a result of basically adding water to an alkene in this case. We have to give the location of the OH like our double bonds and triple bonds, because we could have the OH on the first carbon here, which would be 1-propanol, which is a different alcohol. 2-propanol is also isopropyl alcohol. That's a CH3CH3. It's also a rubbing alcohol, right? So a bunch of fun names for the same thing, basically. Now, this works as well for things that are not water. So you could have, in this case, for example, let's do let's do kind of a shorter one here. If we added our HBr, actually, we'll do the same one. Let's put a fix my structure here in a second here. Get rid of some hydrogens as I over bonded it there. Let's get rid of that there, and that looks good, I think. All right, so let's say we do the same thing with HBr. This would also be an unsymmetrical addition. It works the same way. Again, we're going to basically draw this exact same thing exactly the way it is. We're going to change our double bond into a single bond to make room for what's coming in. And in this case, we actually end up the same, which is our hydrogen is going to come in and our Br is going to come in. And the hydrogen would end up over here. I'll just circle it to say that's the one that came in. And obviously our Br would go in this case. And in this case, again, an unsymmetrical addition. So an unsymmetrical addition happens when you add hydrogen and something else like HOH, like water, hydrogen and Br, like hydrogen bromide, hydrogen chloride. So you just have to worry about where the hydrogen ends up. Now, if there is no difference, for example, the one I originally had that I just erased, if you happen to be adding this to this guy, there really is no difference in the number of hydrogens that each of them start with. So it doesn't make a difference where you put them. You could put the H on either one or the Br, for example, on the other one, or the OH on either one as well. Question on addition reactions. Again, doesn't matter if there's like a big old chain, doesn't matter if it's a smaller chain, doesn't matter if it's one of these guys, it doesn't. Yeah, so what would I get if I did this guy? And what would I get if I did not that guy? What would I get if I terribly draw that? I'm just gonna keep drawing shapes here. Let's just do that. Let's do this. All right, draw what you. This should be the only place of concern for me. I'm going to do the same thing I did with the other, even though it's a ring. I'm just going to make it into a single bond. Once again, nothing fancy happens, like it opens up or anything like that. It stays closed, by the way. And I can get rid of the double bond to make room for it. And frankly, that's actually the answer right there, because when I did that, I now have one hydrogen that can come in and two hydrogens that come in, and we could just say those are the two. It had one hydrogen in each of those locations to start with anyways, right? So those would be coming in there. Here again, we would go here as our important spot. We're going to make that into a single bond all the way around. When we add water, that is H and OH. In this case, when we look at this guy originally had one hydrogen. This guy originally had one hydrogen. There's really no difference in the number of hydrogens. So even though this is unsymmetrical, it doesn't really matter where you put which one. But somebody should end up with an OH at the end of it there to make our cyclopropanol alcohol right there. Yeah, so a little cyclopropanol in this case. And again, obviously, you don't, since it's line structure, you don't have to draw it. But again, our H basically ended up back there on that backside. Question on that there.